Hi everybody, I'm the co-founder of ClimeRocks, which is a French startup dedicated to developing ERW in France. And what we are doing in ClimeRocks is removing CO2 with rocks, which is the topic with ERW. Daniel said some words about it, but why we're here? Because we faced a big challenge, which is climate change and global warming. And we will need a lot of ingenuity and a lot of solutions to face it. And ERW could be a good solution to play a role in mitigate our anthropogenic emissions. And which is amazing, it's the chemical weathering of rocks was discovered by a French scientist 180 years ago, Jean-Jacques Ebelman in Paris. And now we are trying to leverage it to absorb and remove CO2. Yes, because releasing will not be enough. Daniel said it earlier. We'll need to remove gigatons of CO2. And actually, you can see on the screen we are here. And even if we reduce drastically our emission that we should do right now, there will be a gap, and we'll need to have net negative emission technology for doing that, and ERW could do that. But CO2 is not the only problem, because EU soils, for example, are largely degraded. It's around 70% of the soils that are threatened in Europe, and which is the corollary is the food insecurity that can generate, because if our soils are not in good health, it could have an impact on the crops. And on the ocean part, ocean play a key role in absorbing CO2 from the atmosphere, and so they get more and more acidified, which generate a biodiversity loss. So the CO2 is not the only challenge, and ERW can play a role for addressing all those problems. So at ClimeRocks, we are doing ERW in France. You can see on the left corner one of our field trials we have done on mice field. We tried 2 rock application rate, one with 0, which is the control, and one with 10 tons per hectare, and the other one with 50 tons per hectare. You can see a basalt pile there, which is coming from the quarry nearby. The machinery we use for spreading, and one of the quarry. We are operating in the Massif Central, which is a former volcanic region in France. There is a lot of basalt quarry there, and we made a custom MRV to monitor the CO2 removal. ERW, it's interesting because it's a mean to sequester permanently and reliably the carbon and put back the carbon into the geosphere. As Daniel said earlier, if you grow trees, it's only temporary. Unlike in ERW, you put the carbon back into the ocean and in the sediments, and it's much more durable. It's highly scalable because it leverages alkaline rocks, and notably basalt. And basalt is a rock you can basically find everywhere because it's part of the Earth's crust, and it has a big benefits on soil health, notably on pH, and the nutrients are released when the rock gets dissolved. So finally, it's an opportunity for farmers because it's traduced in better crop yields. But to monitor all the co-benefits and the CO2 removal, you have to deal with a lot of science behind. And what I try to represent on this screen is the multidisciplinary approach we use at ClimeRocks to see to follow the CO2 removal on the whole life cycle of our bicarbonates. So it begins with soil science. Soil science is key because the reaction is happening in soil, and there is key parameter linked with the soil due to the microbiology and the microorganism in the soil, which can influence the pH, for example, with and the CO2 partial pressure with the respiration. The weather is key because if, for example, it's not raining or it's the climate is cold, you will have effects on kinetics, and it results in benefits and effects on agronomy because basically you are remineralizing the soil, and so the soil is in better health, and so you get more crops. Geology is part of the equation because you need to characterize your feedstock, account for the geomorphology, and geochemistry is at the center of the things. And then you are until once the bicarbonates have been created in the soil, they get leached out with the water, and you have to take into account the riverine system for transportation, and at last, when they go to the sea, the aspect of the carbonate system of the ocean. So, which is the Earth modeling could be useful, for example, to simulate the concentration of carbonate in the ocean. So, for the point of view of a young startup, and we are only two at ClimeRock, it's a lot of science to deal with, and you need to be to have a global understanding of all that to have a robust NRV. Okay. So for the soil part, bicarbonates, as I said, are created in the soil, and you can see there the reaction of chemical weathering, which is happening between the carbonic acid and silicate rock powder. There is key factors there, and the soil moisture, the dry and wet cycle in the soil make that carbonic acid and the CO2, as we've seen just on the previous slide, is a lot of influenced by the respiration of soil. And then you have these cations and these bicarbonates who are splitting in these three phases, which are where we make the soil mass balance, accounting for seeing how much the CO2 we remove. The bicarbonate can precipitate, so it's a lot of phenomenon occurring at the same time, and to track all that, it's really hard. And that's why I call it a critical zone process, because it's really in an ecosystem where the chemical weathering occur, and it's not in the lab. So the kinetics are really, really different. And there is this challenge on carbonic acid, because in the field, sometimes you have nitric acid, sulfuric acid, and so on, and they can weather your basalt without making CO2 removal. So it's a key aspect to account. So that's why we make our MRV, a really careful feedstock characterization for mineralogy, which is important for kinetics, chemistry, which can derive the CDR potential, how much carbon you can capture with your rock, and the grain size, which is very important. Soil sampling for example, CC, cations, pH, and all stuff, and pore water sampling, because as we've seen on the previous slide, there is some bicarbonates we are in water. But it's not only the soil work we have. We need to track our bicarbonate exported in all the watershed, because we are working basically at ClimeRock for the moment in this area of France, so at the south of Clermont-Ferrand. And you know, we are in the big watershed of La Loire. We can see this kind of equation we use for trying to assess the possibilities that our bicarbonates dissolved precipitate at some point of the river. Yeah, you can see the estuary, which is the mix between the sea and the river. The salinity is varying, and you have hydrology aspects to take into account. In France, we have data, but you have to consolidate all the stuff to have a monitoring of the process and the riverine transport. Being an ERW developer, it's not easy because you have to juggle with a lot of operational constraints. For example, soil acidity, with nitric acid, sulfuric acid, other type of acid which is not non-carbonic, the spreading stuff, because, for example, farmers are using a lot limestone, and when they use limestone on their field, it's about 1 or 2 ton per hectare. And basically in ClimeRocks, we are using 10 to 20 tons per hectare. It's not the same amount to spread, so they don't necessarily have the equipment and the machinery for doing that. So it's new for them because it's rock, it's not carbonates. So you have change management to do. Distance is equally an aspect really important, because if you carry the basalt on a distance too far, it will discount your CO2 removal carbon certificates. The kinetics are key and really changing for a developer for us, because we said to one customer, okay, we will capture this amount of CO2 during this time frame. But if the condition, the weather condition, the soil condition change, and we can't, if we make a mistake at evaluating the kinetics, it can be have a repercussion on our activity. And at least one quick point about the economics of ERW. At the time in 2023, we were at an average price for the ERW ton of CO2 removal around $371. And when you compare with basic classic carbon offsets, for example, afforestation, blue carbon, and stuff, or cook stuff, you see we are around 10 euros per ton, which means that for corporate buyers, it's a big gap in terms of pricing. And one of key challenge for us as scientists and engineers is to bring down this cost to have a bigger impact, because the companies are limited for buying some big volume due to the price, which is quite higher compared to the basically traditional biosphere project. Actually, its ERW ton is 40 times higher in terms of price than the conventional carbon offset. So we need to make smarter systems for MRV to diminish the cost. Thank you.